Hello, everyone. My name is Wong Hoi Lam, and today I'm going to present my final year project progress. And my final year project is OpenLane RISC-V design, and my supervisor is Professor Ray Chang, and my assessor is Professor Aston McCoy. And the main objective of my project is to design and implement a high-performance RISC-V R32i CPU. The processor will support the full R32i instruction set, and the architecture will be developed progressively, starting from a single cycle CPU baseline, and then extending to a 5-stage pipeline, and integrating the cache, and eventually move on to the superscalar version. And each phase of the project will enforce RTL design, comprehensive verification, and generation of the physical layout using the OpenLane ASIC flow. And this is the development roadmap. And I have already completed phase 1, which is the single cycle CPU design. And now I'm on phase 2, the 5-stage pipeline CPU. And for the rest of the phase, they are the cache integration to integrate the data cache and the instruction cache. And the phase 4 is the superscalar to implement the dual issue. And for the dual issue, I will implement the partially dual issue in order design instead of fully dual issue out of order design due to the time limit. And phase 5 is the final physical design using the OpenLane flow. And for the background and the methodology, the design work, let me introduce some background. The RISC-V, it is an open source architecture with growing industry adoption and ecosystem support. It is one of the most popular architecture. And also the OpenLane flow, it is a completely open source ASIC implementation toolchain. It can be used for generating the GDS file, the GDS layout, the manufacturable GDS layout from the RTL design. And for the RTL design, I use the Verilog HDL to implement the design. And I use a simulation to do the functional verification. I use Verilator for the simulation, and I use a GTK wave for the waveform analysis. And for the benchmarking is performed with the standard tests, including the Hello World.c, including the Hello World C program and the CoreMark benchmarking C program. And this is the current development status. For the single cycle CPU, I have completed the implementation with support for all the R32i instructions, the 40 instructions, and also including one control and status register, the M cycle. And I also implement a 128 kilobyte instruction and data memory, which are only simulation purpose only to run the CoreMark. For the OpenLane flow, I use a much more smaller memory. And also I implement a 32 registers. I also implement the UARTs implement the memory map IO UARTs to show the testing result. And I do all the functional verification pass, and all the test cases is passed. And for physical implementation, the design is successfully passed the OpenLane ASIC flow, and it achieved 100 MHz maximum frequency. However, there's some limitations. I will talk about it afterwards. And the GDS2 layout is also generated. And for the pipeline CPU, it is currently in progress. And next, let me to talk about the my single cycle CPU. For my single cycle CPU, there includes the core modules. For example, the program counter, instruction fetch unit, instruction decoder, and execution unit, which is the ALU. And for the memory, it is a Harvard memory, which the instruction memory and the data memory are separated, and both of them are byte-aligned access memory. And for the instruction, it supports the arithmetic and logic instructions, and load and store instructions, branch and jump control, and also the CSRM cycle, which more than 40 instructions are supported. And this is the detailed CPU system architecture. This capture is generated by the Vivado software. And for this single cycle CPU, the data flow is simple. The CPU first, it will fetch the instructions, fetch the program from the instruction memory according to the PC value from the PC register, and it will pass the instructions to the instruction decoder, and to decode the instruction and to pass the result to the execution unit, which is also the ALU, to do the computation. And after the computation, it will pass some mux to determine the data path, and to pass it to the write back, let the write back unit to determine the write back path. And next, let me to introduce some result. I run the Hello World C program on my design. I first compile my Hello World C program into machine code, which is the hex file using the RISC-V GCC toolchain. And I load the hex file into the instruction memory using the Verilog, read memory statement. And this is the result of the Hello World C program. Like you can see that the Hello World is successfully printed out. And next is the core mark benchmarking results. I run the core mark on my CPU, on my design and the test, and I achieve 1.15 core mark per megahertz. And I achieve 46 iterations per second. And you can see that the result here is 46 iterations per second. And I set my CPU to 40 megahertz because it is more practical for a single cycle CPU instead of the result from the OpenLane, the 100 megahertz. And to use this 46 to divide by the 40, and I will get the 1.15. And I also check, and I also do some comparison to some existing processor. And I found that the most similar processor, the most similar result is the STM32F103 CAT6. And you can see that the core mark per megahertz is 1.13, which is quite similar to my existing design, 1.15. And my design is already exceed the performance of the Arduino Mega. However, this result is a bit optimistic due to the purely combinational memory because it is a single cycle CPU. And the combinational memory, it don't have any latency. So it is not that practical in real life. So the real performance will be not that high. And I also do the OpenLane physical design. I put my CPU to the OpenLane. And these are the synthesis outcomes. I achieve the maximum frequency of 100 megahertz in the post-synthesis timing analysis. And this is the timing report. And it shows that I achieved the timing requirements. You can see that the total negative slack and worst negative slack, they are both 0, which means I reached the timing requirements. And you can see that the setup and hold slack of the design is positive, which is also good. It means there are some margins to reach the timing requirements. And I also generate a GDS layout, and I also do the pass all the DRC requirements for a target process. And as I have told before, this 100 megahertz frequency is a bit optimistic due to the combinational memory modeling in the current design. So in future phases, I will incorporate realistic memory macros with the proper timing models for my pipeline CPU. And this is the GDS layout generated by the OpenLane. And if you zoom it in, you will see that there are the CMOS here, and there are some contacts. These are some contacts. And I open this GDS file using the K layout. So this is the interface of the K layout, and you can see the layout of the chips of the chip. And this is the implementation progress overview, just like I have told before. I've already completed the single cycle CPU RTL design and do the verification and benchmarking, and also do the OpenLane flow physical design. And currently I'm in progress of my 5-stage pipeline CPU. And I also face some technical challenges through the development. And I have told it before, the current 100 megahertz F frequency max, the maximum frequency is overestimated due to the combinational memory. And to solve this, I will integrate the proper memory macros in the future. And next is the OpenLane uses. The uses over-optimize the design. I found that the uses in the OpenLane flow will flatten the design and remove the essential logic if the top modules does not have declared the outputs. And to solve this, I explicitly define the outputs in the top modules to preserve critical modules. So I just define a PC out port to avoid the uses to flatten the design. And by moving on to the pipeline version of my CPU, I found that the previously verification method is inefficient. Previously, I manually compared the register by running the same assembly program on the Phoenix RISC-V online simulator and on my design. And this manual process is inefficient for the future development because I need to check the values manually. And to solve this, I'm considering to adopt an offline golden model, or just use my single cycle CPU as a golden model, and develop a Python script to automatically compare the logs, to compare the register automatically, to streamline the verification process in order to save more time. And for the next 2 months, I'm going to complete the pipeline CPU RTL design with at least 70% of the progress target, and implement the hazard detection and forward units, and do all the functional verification and the OpenLane backend flow for the pipeline version. And then I will continue to integrate the instruction and data catch and complete the verification, and also do the performance analysis, and also do also pass the OpenLane flow again to check the frequency and also other constraints. And those are the key achievement summary. To sum up, I've completed the single cycle CPU design with full instruction set support, the full R32R instruction set, and I have validated through comprehensive testing, and I also successfully passed my single cycle CPU to the OpenLane ASIC flow and generated the GDS layout, and also pass all the verification test case. And currently I'm in the progress of the pipeline. And that's the end of my presentation. Thank you.